Good evening, professors. I'm YAO Jingrui, student ID USM24100973. Today I will present my project titled "A Predictive Analysis Method of Software Review Statement Classification Based on Machine Learning for Mobile Application Development Comparison." I will walk you through the basic idea, the methods very briefly, and then focus more on the main results and what they mean for real companies. This slide is just a quick overview of what I'm trying to do. In short, my goal is to build a machine learning system that can automatically classify app reviews as positive, neutral, or negative, and that small and medium companies can actually use in practice. Based on that, I set a few research questions about how to design the features, which models work best, how to deploy the system, and what benefits it can bring. I will go into those in the next slides. Here is the whole project in few sentences. I fill the CRISP-DM framework and use traditional machine learning models to analyze Google Play app reviews. The best model turns out to XGBoost using TF-IDF n-grams plus some simple extra features like review length and star rating. On a three-class task, positive, neutral, and negative, the model reaches about 89.2% accuracy and 88.7% macro F1, which is higher than my 85% target and clearly better than the 73% manual accuracy I use as a reference. The system can be wrapped as a REST API and connected to a dashboard, so an SME can get insights from thousands of reviews in minutes, instead of waiting days for manual analysis. This slide explains why the project matters. App stores collect a huge amount of reviews. For many small or medium app developers, people still read the tag reviews by hand. That's slow, trying, and not very consistent. On the other hand, a lot of research use deep learning models. They are powerful, but they need GPUs, complex code, and specialist skills, since many SMEs don't really have. So my main objective is to fill this gap, build a statement analysis system that is accurate enough, but still simple and cheap enough for SMEs to deploy and maintain. From that goal, I ask 5 key questions. Number 1, for text features, what kind of feature engineering works best for app reviews? Number 2, among traditional models, which algorithm performs best for 3-class statements? Number 3, how can we make the system practical for SMEs in terms of speed, cost, and interpretability? Number 4, how should we deploy it? For example, through APIs or dashboards, so non-technical staff can use it. Number 5, compared with manual work, how much time and money can be saved, and does it help decision making? This question keeps the work grounded in real-world use, not just theory. Now, quick look at the methodology, which is Chapter 3. I follow CRISP-DM business understanding, data preparation, modeling, evaluation, and deployment. The data comes from Google Play reviews tested on Kaggle, around 250,000 English reviews after cleaning. I label statement using stars 4 to 5 stars equal positive, 3 stars equal neutral, 1 to 2 stars equal negative. Then I clean the text, lowercase, organizer, remove star words and general words like app, and apply limitation. For features, I use TF-IDF, UNI, BAI, and TI-GRAMS, plus simple mutual features like review length and star rating. I test 5 models: neighbor-based, logistic regression, linear SVM, random forest, and XGBoost. I use a split, create siege with 5-fold cross-validation, and handle class imbalanced with balanced with width and smooth. With the stuff in mind, we can look at the main results. This slide shows the overview statement distribution in the datatest. After pre-production, about 58% of reviews are positive, 30% are negative, and only around 12% are neutral. So the data is clear imbalances. A cell model that always predicts positive would already get 58% accuracy. That's why I asked her look at macro F1 and not just accuracy. It also explains why the neutral class is harder. There are few neutral reviews, and the language is usually least clear. Here we can see the most frequent words in positive and negative reviews. Positive reviews are full of words like excellent, great, love, easy to use, useful, fast, helpful. Negative reviews have words like bug, crash, slow, problem, terrible, waste, money, broken, unusable, worst. The difference is quite obvious. This tells us the text carries strong sentiment signals and supports using n-grams to capture phrases like easy to use or waste of money. For practice, this also gives product teams a quick idea of what users like and hate. For example, repeated motions of cash and slow. This slide compares the 5 models on the test sheet. All of them beat the 58% baseline, but with different levels. Nail-based is fast but only in the low 8% accuracy range. Logistic regression and linear SVM reach the high 8% range. Random forest is close but not the top. XGBoost is the best, with about 89.2% accuracy and 88.7% macro F1. So XGBoost becomes my final chosen model. It has the largest express TF-IDF feature space where and still runs efficiently on normal headway. Here we have 2 parts, the conclusion matrix for XGBoost and an elevation study. From the confusion matrixical, we see the model is very good at recognizing positive and negative reviews. Most mistakes happen with the neutral class, which is expected because neutral language is more suitable and we have few examples. The evaluation study shows that using only unigrams gives worker results. Adding bgrams and trigrams helps a lot. And adding meter features like star ratings and review length brings future boost. The final combination n-gram TF-IDF plus measure fits with XGBoost gives a boost balance between performance and complexity, which is important when deploying it in real company. This slide sums up the main recommendations and contributions. First, an end-to-end CRRSPDM pipeline is the sole way to handle APP reviews, from raw data to decision support dashboards. Second, among the test models, XGBoost is the recommended choice. It seems the 89% accuracy mark and clear beats manual library in my SME scenario. Third, good feature engineering real matters. TF-IDF grams plus simple meta features can get close to deep learning performance without the cost and complexity. Finally, in business terms, the system can cut processing time for 7 to 10 days down to minutes, improve accuracy from around 73% to almost 90%, and be deployed as a REST API and this dashboard that feeds into existing tools, like ticketing and analysis systems. To wrap up, this project shows that traditional machine learning, if designed carefully, can provide a critical and powerful sentiment analysis solution for mobile app developers, especially small and medium companies. It addresses the gap I described in Chapter 1, and the results in Chapter 4 and 5 show clear improvements in both accuracy and efficiency with manual review analysis. Thank you very much for listening.